What is modus ponens?
The Latin term modus ponens means mode that affirms. Or in the case of logic, stands for the rule of detachment. This rule, also known as a rule of inference, pertains to the if-then statement and forms the basis of most proofs. If P then Q, or if P is true, then the conclusion Q is true. It is often seen as the following: if P, then QP. Therefore, Q. To see this another way, P and Q, if it is raining, then there are clouds in the sky P, it is raining Q. There are clouds in the sky. There are several ways to break down the modus ponens. The argument form has two premises, the if-then, or conditional claim. Or namely that P implies Q, and that P, called the antecedent of the conditional claim, is true. From these two premises it can be logically concluded that Q, called the consequent of the conditional claim, must be true as well. In other words, if the antecedent of a conditional is true, then the consequent must be true.
How did people in the Renaissance approach architecture?
During the Renaissance, not only mathematics but also architecture made great strides. In particular, church buildings were no longer based on the shape of the cross, but rather on the circle. This is because Renaissance architects believed that ancient mathematicians equated circles with geometric perfection, and that the circle must then represent the perfection of God.
What is the Hertzsprung-Russell diagram?
The Hertzsprung-Russell diagram is a two-dimensional graph of the mathematical relationship between the absolute magnitude, luminosity, stellar classification, and surface temperature of star Sol, resulting in a diagram of the stellar life cycle. It was plotted by Danish astronomer Ejnar Hertzsprung. 1873196 in 1911 and independently by American astronomer Henry Norris Russell, 1877 to 1957, in 1913.
How are probabilities of compound events determined?
Besides the probability of simple events, probabilities of compound events can also be computed. For example, if x and y represent two independent events, the probability that both x and y will occur is given by the product of their separate probabilities, and the probability that either of the two events will occur is given by the sum of their separate probabilities minus the probability that both will occur. For example, if the probability that a certain man will live to be 70 is 0.5, and the probability that his wife will live to be 70 is 0.6, the probability that they will both live to be 70 is 0.5 x 0.6 equals 0.3. the probability that either the husband or wife will reach 70 is 0.5 plus 0.6 0.3 equals 0.8.
How do functions pertain to sets?
A function in sets pertains to a correspondence between two sets called the domain and range. Each member of the domain has exactly one member of the range. It is often called a many-to-one, or sometimes one-to-one, relation. For example, f equals 1, 2, 3, 6, 4, minus 2, 8, 0. 9, 6, is a function, with each set of numbers being an ordered pair. This is because it assigns each member of the set 1, 3, 4, 8, 9 exactly one value in the set 2, 6, minus 2, 0, 6. It never has two ordered pairs with the same x and different y values. In this case, the domain is 1, 3, 4, 8, 9, and the range is 2, 6, minus 2, 0, 6. To show an example that is not a function, f equals 1, 8, 4, 2, 3, 5, 1, 3. 6, 11, is not a function because it does not assign each member of the set exactly one value, it assigns x equals 1 to both y equals 8 and y equals 3, or it has two ordered pairs that have the same x values to two different y values, 1, 8, and 1, 3. For more information about functions, see algebra.
What are some mathematical concepts used in demography?
Demography is the statistical study of human populations that reveals the characteristics of the population. This includes such factors as size, density, growth, distribution, and vital statistics. Some common demographic statistics include birth and death rates, life expectancy, and infant mortality rates. The birth rate, also called the crude birth rate, is usually represented in demography as the ratio of live births in an area population annually. Most often expressed as the annual number of live births per 1,000 people, or a time division, such as at mid-year. Related to this is the infant mortality rate, which is the annual number of deaths of children less than 1 year old per 1,000 live births. The death rate, or crude death rate, refers to the ratio of deaths in an area population annually. It is often expressed as the annual number of deaths per 1,000 people. Life expectancy is related to death rate and indicates the average lifespan of people within a certain population. It is calculated on the basis of statistical probabilities, usually represented by the average number of years a group of people born in the same year can be expected to live. If mortality at each age remains constant in the future.
What was the difference engine?
because of its automatic sequential approach. The difference engine is thought of by most mathematical historians to be the precursor to modern computers. Johann H. Müller, an engineer in the Hessian Army, first developed the concept in 1786. His idea was to have a special machine that would evaluate and print mathematical tables by adding sequentially the difference between certain polynomial values. But he could not get the funds to build the machine. Müller's idea was soon lost before it was resurrected in 1822, when Charles Babbage obtained government funds to build a programmable, steam-powered prototype of Müller's device. For more information about Babbage, see below. Because of technical limitations, funding cuts, and Babbage's interest in a more advanced device of his own design, Müller's difference engine was only partially completed. Eventually, Swedish inventors George Scoits, 1785–1873, and his son Edvard, 1821–1881, would in 1853 build the difference engine, the first calculator with the ability to print.
What new ideas came out of Einstein's, and others, study of relativity?
He showed that space and time could no longer be viewed as separate, independent entities, forming a four-dimensional continuum called spacetime, also written as spacetime. It is not easy to verbally explain the intricacies of Einstein's theory. The best way to interpret his works is with the use of formulations from certain mathematical branches, such as tensor calculus. For more about tensors, see mathematical analysis. But such complex equations are beyond the scope of this book.
How can I prove that 1 equals 0?
There is a way to show that 1 equals 0. And it includes an interesting proof. Consider two non-zero numbers x and y such that x equals y. If that is so, then x2 equals xy. Subtracting y2 from both sides gives x2 y2 equals xy y2. Then dividing by xy gives x plus y equals y, and since x equals y, then 2y equals y. Thus 2 equals 1, the proof started with y as a non-zero, so subtracting 1 from both sides gives 1 equals 0.
How are modern abaci used?
Today's standard abacus is typically constructed of wood or plastic and varies in size. Most are about the size of a small laptop computer. The frame of the device has a series of vertical rods or wires on which a number of wooden beads slide freely. A horizontal beam separates the frame into two sections called the lower and upper decks. For example, in a Chinese abacus, the lower and upper decks each have 13 columns. The lower deck has 5 beads per column, while the upper deck has 2 beads. Each bead on the upper deck has a value of 5. While each bead on the lower deck has a value of 1, thus, it is called a 1/5 abacus. To use the abacus, users place the abacus flat on a table or their laps. They then push all the beads on the upper and lower decks away from the horizontal beam. From there, the beads are manipulated, usually with the index finger or thumb of one hand, to calculate a problem. For example, if you wanted to express the number 7, you would move 2 beads in the lower deck and 1 bead in the upper deck. 1 plus 1 plus 5 equals 7. This modern abacus is still used by shopkeepers in Asia and many so-called Chinatowns in North America. Students continue to be taught how to use the abacus in Asian schools, especially to teach children simple mathematics and multiplication. In fact, it is an excellent way to remember multiplication tables and is useful for teaching other base numbering systems, because it can adapt itself to any base. For more about base numbers, see History of Mathematics and Math Basics.
What is a numeral?
A numeral is a standard symbol for a number. For example, X is the Roman numeral that corresponds to 10 in the standard Hindu-Arabic system.
What is meteorology?
Meteorology is the study of atmospheric phenomena, their interactions and processes. It is often considered part of the earth sciences and is most commonly associated with weather and weather forecasting.
What were some early measurements of weight?
Some of the early measurements of weight include the grain, pound, and ton. Ancient peoples used stones, seeds, and beans to measure weight. But grain, such as wheat or barley corn, was a favorite. In fact, the grain, abbreviated GR, is still one of the smallest units of weight used today. To compare, 1 pound equals 7,000 grains. The traditional pound as a unit of weight was used throughout the Roman Empire. But like many other measurements over time, the number of ounces in a pound seemed to shift and change. For example, the number of ounces in the Roman pound was 12. European merchants used 16 ounces to the pound. Eventually, 16 ounces in a pound became standard. For more about ounces, see below. Back in the 19th century, the Americans who did not like the British larger weights decided that a hundredweight would equal 100 pounds, the British hundredweight was 112. This meant a ton was equal to 20 hundredweight for the American ton, or the Americans' short ton was 2,000 pounds. While the British long ton of 20 hundredweight was equal to 2,240 pounds. There were, of course, debates, but not everyone disagreed with the American short ton. It became the favorite of British merchants, who called it a centile. Eventually, the ton on the international market went metric. And today a metric ton is close to the original British long ton. It is equal to 1,000 kilograms, or approximately 2,204 pounds, and is officially called a ton. Although the international system, SI, CP 50, standard uses ton, the United States government recommends using the metric ton.
What are the various types of quadrilaterals?
There are several types of quadrilaterals, which are polygons with four sides. Interestingly enough, some definitions can be combined, for example, if a quadrilateral is both a rhombus and a rectangle, it is truly a square. The following lists the common quadrilaterals. Square. The most obvious quadrilateral is the square. It is an equiangular quadrilateral with four right angles. It is also defined as having four congruent sides. Rectangle. The second most well-known quadrilateral is the rectangle, a quadrilateral with four right angles, with the opposite sides parallel and congruent, and opposite angles congruent. Parallelogram. A parallelogram is a quadrilateral with both pairs of opposite sides parallel. Thus, opposite sides and angles are congruent. Rhombus. A rhombus is a parallelogram with four equilateral, or congruent, sides. Trapezoid. A trapezoid is a quadrilateral with exactly one pair of parallel sides. This is also seen in books as a quadrilateral with at least one pair of parallel sides. But this latter definition is often debated among mathematicians, as the meaning is not the same as the first statement. With trapezoids, the parallel sides are called the bases, the non-parallel sides are called the legs. Isosceles trapezoid. An isosceles trapezoid is one with non-parallel sides that are equal in length. Or a trapezoid with a pair of equiangular base angles. The legs of an isosceles trapezoid are congruent. For more about these figures, see elsewhere in this chapter.
What happened to the Babylonians?
After the Amorites, a Semitic people, founded Babylon, there were several dynasties that ruled the area, including those associated with the famous king and lawmaker, Hammurabi, 1792 to 1750 BCE. It was periodically taken over, including in 1594 BCE by the Kassites and in the 12th century BCE by the Assyrians. Through all these conquests, most of the Babylonian culture retained its own distinctiveness. With the fall of the Assyrian Empire in 612 BCE, the Babylonian culture bloomed, at least until its conquest by Cyrus of Persia in 539 BCE. It eventually died out a short time after being conquered by Alexander the Great, 356 to 323 BCE. In 331 BCE, ironically, Alexander died in Babylon, unable to recover from a fever he contracted.
What is the integral calculus?
The integral calculus is the part of the calculus that deals with integrals, both the integral as the limit of a sum and the integral as the antiderivative of a function. See below for more information. In general, the integral calculus is the limit of a sum of elements in which the number of the elements increase without bound, while the size of the elements diminishes. It is also considered the second most important kind of limit in the calculus. The first being limits in association with derivatives. It was originally developed by using polygons to approximate areas of geometrically shaped objects such as circles.
How do you simplify an algebraic equation?
The best way to simplify an equation is to combine like terms, which makes the equation simpler to solve. Numbers may be combined, as well as any terms with the same variable. Terms can be combined either by adding or subtracting variables of the same kind. One can also use multiplication and division to simplify an equation. By multiplying or dividing each side by the same number, except 0. The following are some examples. Adding like terms: 4x plus 3x equals 14, simplifies to 7x equals 14. The equation 4 plus 8x plus 10 4x2 equals 20 can be simplified by combining the like terms, which gives the simplified result 12 plus 4x equals 20. If necessary, do a combination of addition, subtraction, multiplication, or division. For example, the equation 2x2 equals 4x plus 3, simplifies to 2x equals 4x plus 5, by adding 2 to both sides. Then subtract 2x from both sides, simplifying to 0 equals 2x plus 5. Note, since subtracting any number is the same as adding its negative, it is often more helpful to replace subtractions with additions of a negative number. Finally, subtract 5 from both sides, or 2x equals minus 5. Divide both sides by 2, and the result is x equals minus 5 halves, or minus 2.5. To simplify expressions raised to a power, certain rules should be followed. For example, for x plus 3, 2 4x, square x plus 3, or x plus 3, x plus 3, first squaring the first term. X squared equals x2, then the second, 3 squared equals 9. Then multiply and add the inner and outer terms together, 3x plus 3x equals 6x. By combining like terms, the entire equation results in the simplified expression x2 plus 6x plus 9 4x, which finally equals x2 plus 2x plus 9.
What is Russell's paradox?
Russell's paradox is one of the most famous of the set theory paradoxes. It first appears when studying the naive set theory. In this case, R is the set of all sets that are not members of themselves. From there, R is neither a member of itself nor not a member of itself. The paradox sets becomes evident when one tries to reason how a set appears to be a member of itself if and only if it is not a member of itself. Discovered by Welsh mathematician and logician Bertrand Arthur William Russell. 1872 to 1970, in 1901, the paradox sparked a great deal of work and controversy in logic, set theory, and especially in philosophy and foundations of mathematics. The reason why it became so important was its effect on mathematics. It created problems for those who based mathematics on logic. And it also indicated that something was wrong with George Cantor's intuitive set theory. For more about Russell and the paradox, see History of Mathematics.
What is geology?
The word geology comes from the Greek geo, meaning the earth. And the ology suffix comes from logos, meaning discussion. Overall, geology is considered to be the study of the earth. In modern times, thanks to space probes reaching into the solar system, geology also now entails the surface features on other planets and satellites.
What is abstract algebra?
Abstract algebra is a collection of mathematical topics that deal with algebraic structures rather than the usual number systems. These structures include groups, rings, and fields. Branches of these topics include commutative and homological algebras. In addition, linear algebra and even elementary number theory. See Math Basics, are often included under abstract algebra.
What are equations?
In its simplest form, an equation is represented by expressions written with an equal sign in between. The two entities on either side are equal to each other. They are among the simplest mathematical problems most people deal with. Most people have solved equations in their daily lives without realizing it. For example, when students first learn addition in school, they typically work on equations such as plus 5 equals 7, in which the blank needs to be filled. This problem could also be expressed as x plus 5 equals 7, a simple equation. In this case, the equation is solved when x equals 2. The following are also equations. 6 equals 6x equals 8y plus 8 equals 14x 4 equals 15x 5xy equals 8xy 2 plus 4. There are also some fundamental properties of equations that are good to know. They include symmetric properties. If A equals B, then B equals A. Substitution, if A equals B, then A may be replaced by B. Addition, if A equals B, and C is a number, then A plus C equals B plus C, and multiplication, if A equals B, and C is a number, then AXC equals BXC.
What do the numbers on an aneroid barometer signify?
The non-liquid aneroid barometer measures air pressure. As the atmospheric pressure changes because of storm systems or lack of storms, the instrument records the changes. Because atmospheric pressure changes with distance above or below sea level. A barometer can also be used to measure altitude. The aneroid barometer contains a small capsule that acts like a bellows, but with the air removed. When the air pressure increases, the sides of the capsule are pushed in and the connected needle rises, moves clockwise. When the air pressure decreases or falls, the capsule's sides puff out and the needle moves in a counterclockwise direction. The numbers on a common barometer range from about 26 to 31. With divisions of 10 or more in between each number. A needle, actually a hand similar to a clock hand, points to the numbers on the barometer and moves in response to the changing air pressure. These numbers are based on the principle that atmospheric pressure supports 30 inches. 76.2 centimeters, of liquid mercury in a tube with one end sealed. And this information is based on the mercury barometer, the first type ever made.
What is propositional calculus?
Propositional calculus is not the calculus most of us hear about. But it is considered by many to be the foundation of symbolic logic. Actually, the term calculus is a generic name for any area of mathematics that deals with calculating. Thus, arithmetic could be called the calculus of numbers. Also known as truth functional analysis, sentential calculus, or the calculus of propositions. Or, as seen above, any declarative sentence that is either true or false. Propositional calculus deals with statements that can be assigned truth values. In general, it uses symbols to denote logical operators, such as and or, and parentheses for grouping formulas.
What are vertical asymptotes in association with limits?
Using the example above, as x gets closer to 3, the points on the graph get closer to the vertical line x equals 3. Seen as a dashed line on the graph on p. 218, This line is called a vertical asymptote. The above chart shows 4 of the vertical asymptotes for the given function f, x, and their notations.
Is math ever used to solve crimes?
Yes, certain types of mathematics are often used to solve crimes. For example, police officers and crime scene experts use geometry to determine the conditions behind the crime. Angles come in handy to determine from what direction a drop of blood originated. Determine where a car was coming from when it struck another car, or to otherwise reconstruct a crime scene. Length measurements can be used to determine the stride and shoe size of a robber from the person's footprints. Some higher math comes in handy to see how fast a car was traveling. As it slammed on its brakes, a task solved by measuring skid marks. At murder scenes, forensic personnel can measure the splatter pattern of bloodstains on a wall. To determine where the murdered person was standing, or even measure the size and angle of a bullet wound to determine the distance from, and position of, the murdered person to the murderer. Probably the biggest connection between mathematics and solving crimes is how mathematics teaches people to improve their thinking habits. Math is a good way to develop problem-solving skills. And in everyday police work there is always another problem to solve.
Did the Egyptians use fractions?
Yes, the Egyptian numbering system dealt with fractions, albeit with symbols that do not resemble modern notation. Fractions were written by placing the hieroglyph for mouth over the hieroglyph for the numerical expression. For example, 1/5 and 1/10 would be seen as the first two illustrations represented in the box on p. 15 other fractions, such as the two symbols for 1/2, see illustration on p15, also have special signs.
What is a fallacy?
A fallacy is an incorrect result in this case. One arrived at through misleading reasoning when examining a logical argument. One of the more common fallacies in logic is believing incorrectly that if P implies Q is true, then Q implies P is also true. The idea of such invalid arguments was well known in the past, with Greek mathematician Aristotle's syllogisms. An argument was valid if it adhered to all the laws; to be false, it only needed to break one law. Euclid, another Greek mathematician, was known to have written an entire book on fallacies in geometry, but the book has since been lost.
Are ratio and proportion important in cooking?
Yes, ratio and proportion, two major mathematical concepts, are important in cooking, as is addition, subtraction, multiplication, and division. For example, when a recipe calls for 1 cup of flour and 2 eggs, the relationship between these two quantities is called a ratio. In this case, the relationship of cups of flour to eggs is 1 to 2, or 1/2, or 1 to. Any change in this ratio and the recipe's result will not be the same, and the food might not be edible. Another way of looking at cooking and mathematics is when changing the amount of ingredients in a recipe. For example, when a recipe calls for a certain amount of each ingredient, and the cook wants to make half a recipe, everything in the list is divided in half. 2 cups of sugar becomes 1 cup, 1/2 teaspoon of vanilla becomes 1/4 teaspoon, and so on. The same logic applies if the cook wants to double the recipe. But in this case everything is multiplied by 2. 2 cups of sugar becomes 4 cups, 1/2 teaspoon of vanilla becomes 1 teaspoon, and so on.
What are quadrants?
Graphs used in the Cartesian coordinate system are broken down into quadrants, or 4 segments. For example, in a two-dimensional system, the x and y axis with the origin as 0 and the two axes perpendicular to each other form the 4 quadrants. In the top left quadrant, quadrant 2, the x is negative and the y is positive. In the top right quadrant, quadrant I, both coordinates are positive. In the bottom left quadrant, quadrant 3, Cartesian coordinates are both negative. And in the bottom right quadrant, quadrant 4, the x is positive and the y is negative.
What was the original use of Stonehenge?
One of the most famous ancient stone complexes is England's Stonehenge. An impressive engineering and mathematical feat. Several groups of local inhabitants constructed this collection of large and small stones grouped in 4 concentric circles, 2 of which are created by paired upright stones bearing huge capstones between 2950 and 1600 BCE. Based on how the stones line up with various astronomical events, historians believe the entire structure represents a huge, literally monumental, calendar. For example, various stones align with the moon, the full moon's extreme positions on the horizon are marked at Stonehenge, and with the sun, including the summer solstice. It is also thought that the complex served as a place in which ancient rites and rituals were performed on significant days of the year. And it was all built without the help of computers.
Who was Omar Khayyam?
Omar Khayyam, 1048 to 1131. who was actually known as Al-Khayyami, was a Persian mathematician, poet, and astronomer. He wrote the treatise on demonstration of problems of algebra, a book that contains a complete classification of cubic equations with geometric solutions, all of which are found by means of intersecting conic sections. He solved the general cubic equation hundreds of years before Niccolò Tartaglia in the 16th century. But his work only had positive roots. Because it was completely geometrical, see elsewhere in this chapter for more about Tartaglia. He also calculated the length of the year to be 365.24219858156 days, a remarkably accurate result for his time, and proved that algebra was definitely related to geometry.
What is a base in mathematics?
The term base has many meanings in the English language, including several that apply to the field of mathematics. When talking about sets, bases are the open sets whose union forms an abstract entity called a topological space. In geometry, the base represents the side of a polygon or polyhedron that is perceived as its bottom. When referring to an isosceles triangle, the base is the side that differs in length from the other two. Thus, the base angles include the side that is thought of as the base. Algebraists also use the term base to describe either the number used with an exponent to create a power, such as 34 equals 81, or to write the same number as a subscript to a logarithm, such as log 381 equals 4. For more information about logarithms, see algebra. One of the more familiar uses of the term base in mathematics deals with our numbering system, in which a base is a natural number whose powers are added to produce a specific number. For example, using 10 as a base, the number 2583.789 is actually 2x103 plus 5x102 plus 8x101 plus 3x100 plus 7x10 to 1 plus 8x10 to 2 plus 9x10 to 3.
The following lists only a few. How do quantum physicists regard light waves?
Added to the mix of the mathematically rich quantum theory was an idea developed by French physicist Prince Louis Victor Pierre Raymond de Broglie, 1892–1987, who discovered the wave nature of electrons and of particles in general, and also devised a mathematical explanation of the kinetic theory of heat. He determined that not only do light waves often exhibit particle-like properties, but particles also often exhibit wave-like properties. This opened a can of quantum worms. From there, two different formulations of quantum mechanics developed. First was the wave mechanics of Austrian physicist Erwin Schrödinger, 1887–1961, who used a mathematical entity, the wave function, related to the probability of finding a particle in space at a given point. Schrödinger also developed a model of the atom that differed from the traditional Niels Bohr model. Second and mathematically equal to Schrödinger's theory was the matrix. Mechanics of German physicist Werner Karl Heisenberg, 1901 to 1976. Fluid mechanics. This is the study of air, water, and other fluids in motion. It includes the mathematics of turbulence, wave propagation, and so on. Geophysics. This is a geological study with a physics basis. Much of the field is dominated by the mathematics of large-scale movement of materials, such as earthquakes, volcanic activity, and fluid mechanics, for example, underground molten volcanic material. Optics. This is the mostly mathematical study of the propagation and evolution of electromagnetic waves, such as diffraction and the path of light rays. Optics requires a great knowledge of geometry and trigonometry, not to mention complex equations.
What are some simple probability events?
The probability measure of an event is sometimes defined as the ratios between the number of outcomes. There are many simple illustrations of probability events, many of which we are all familiar with. One of the simplest examples of probability is tossing a coin. With a sample space of 2 outcomes, heads or tails. If a coin were completely symmetrical, the outcome would more likely be 0.5, ratio of 1/2, for heads and 0.5 for tails. As we all know, it never comes out that way, which may or may not mean our coins are not in perfect balance. Another example is weather records. Many of us keep track of weather over the years. But if one were to gather all the records for the day of May 10 over 30 years from the Weather Service, one could do some simple probability event measurements. For example, take a fictitious sampling of the cloud-covered days in a certain area for the last 30 years on May 10. Say there were 10 cloud-covered May 10s in 30 years. Thus, the probability measure would be a ratio of 10/30ths to the event that the day will be cloudy on May 10. Insurance tables are also figured out in a similar way. For example, if, out of a certain group of 1,000 persons who were 25 years old in 1900, 150 of them lived to be 65, then the ratio 150/1,000 is assigned as the probability that a 25-year-old person will live to be 65. On the other hand, the probability of such a person not living to be 65 is 850/1,000, because the sum of the two measures must be equal to 1. It is true that such a probability statement is valid only for a set group of people. But insurance companies get around this by using a much larger population sample and constantly revising the figures as new data are obtained. Thus, even though many people question the validity of such broad-brush results, the insurance companies believe that, probability-wise, The values they use are valid for most large groups of people and under most conditions of life.
What are the names of the various base systems?
The base 10 system is often referred to as the decimal system. The base 60 system is called the sexagesimal system. This should not be confused with the sexagesimal system, also called the hexadecimal system or the digital system based on powers of 16. A sexagesimal counting table is used to convert numbers using the 60 system into decimals, such as minutes and seconds.
What is a conclusion in logic?
A conclusion is a statement, proposition, found by applying a set of logical rules, syllogisms, to a set of premises. In addition, the final statement of a proof is called the proof's conclusion. For example, in a statement that includes if, then. The result following the then in the statement is called the conclusion.
How was the standard foot determined?
Whatever the true story, the foot we are familiar with today is equal to 12 inches, 30.48 centimeters. The true standardization of the foot came late in the 19th century. After the United States and Britain signed the Treaty of the Meter. In this treaty, the foot was officially defined in terms of the new metric standards being adopted overseas. In the United States, the Metric Act of 1866 further defined the foot as equal to exactly 1200/3937 meter, or about 30.48006096 centimeters. This unit of measurement is still used for geodetic surveying purposes in the United States, and is called the survey foot. By 1959, the United States National Bureau of Standards redefined the foot to equal exactly 30.48 centimeters, or about 0.999998 survey feet. This definition was also adopted in Britain by the Weights and Measures Act of 1963, thus, a foot, or 30.48 centimeters, is also called an international foot.
What is a number?
The term number can be defined in many ways, including a sizable collection of people or things, and even an indefinite quantity or collection. In mathematics, a number, or numeral, is usually defined as a symbolic representation of a specific quantity or place in a sequence. To most people, the most familiar numbers are 1, 2, 3, 4, 5, and so on.
How is linear algebra used to determine the stability of structures?
Structural engineers use linear algebra a great deal. Mainly because there are numerous equations with many unknowns associated with the analysis of a structure in equilibrium. Most of the time, these equations are linear, even when bending, material deformation, is involved. Linear algebra can also be used for other structural concerns, because it deals with the study of vectors. Vector spaces, linear transformations, and systems of linear equations. Of course, linear algebra is not only used to understand structures. Almost every subfield in engineering uses these types of mathematical calculations. For more about linear algebra and linear equations, see algebra.
What happens when you multiply a matrix by the identity matrix?
When you multiply any n by n matrix by the identity matrix, you get that same matrix back again. Therefore, let the letter I represent the n by n identity matrix, and A represent any other n by n matrix. We then have AXI equals A and IXA equals A. This is much like the situation when using the real numbers, x1 equals x and 1x equals x.
Who was Gregor Mendel?
Austrian monk Gregor Johann Mendel, 1822 to 1884, performed experiments with pea plants. From 1857 to 1865 that eventually led to his discovery of the laws of heredity. Gathering 34 different kinds of peas of the genus Pisum, all tested for their purity. He attempted to determine the possibility of producing new variants by crossbreeding. By self-pollinating the plants and covering them over so there was no unplanned cross-pollination, he determined the detailed characteristics of their offspring, such as height and color. Prior to Mendel, scientists believed that heredity characteristics of a species were the result of a blending process, and that over time various parental characteristics were diluted. Mendel showed that characteristics actually followed a set of specific hereditary laws. He worked out what can be described as a mathematical matrix of the characteristics, thus determining what characteristics were dominant and recessive in the plants. For more about matrices, see algebra. But Mendel had a hard time getting his results published. Even after publication by a local natural history society, his work was ignored. Mendel gave up both gardening and science when he was promoted to abbot. Coincidentally, and amazingly, by 1900 3 different biologists working in 3 different countries, Hugo de Vries in the Netherlands, Erich Tschermak von Seisnig in Austria, and Karl Correns in Germany determined the hereditary laws independently. But they all knew about Mendel's work, graciously giving the credit for the findings to him. Mendel, rightfully, is now commonly considered the father of genetics.
To date, what computer has the top speed in operations per second?
In the 2004 Top 500 list, a ranking of supercomputers by speed. With the results announced early each summer, the top 3 supercomputers were as follows. Note: a teraflop is a measure of a computer's performance, in which 1 teraflop is 1012 operations per second. IBM's Blue Gene/L 70.72 teraflops, NASA's Columbia 51.87 teraflops, NEC's Earth Simulator 35.86 teraflops. One of the next contenders is Sandia Labs' Red Storm, with 41.5 teraflops. This list will continue to change each year as more advanced technology becomes available. In actuality, the fastest computer in the world is the human brain. An amazing computing device with the best processor on Earth. To compare, the fastest computers measure speed in trillions of operations per second. But scientists speculate the brain can handle 10 quadrillion operations per second. The actual numbers are probably even higher than that.
How is mathematics important to electrical engineering?
There are many branches of mathematics that are important to electrical engineering. For example, abstract math is used in communication and signal processing. Complex differential equations solving equations involving derivatives are used in circuit theory and systems design. Also in circuit theory, engineers need to know algebra and trigonometry. Engineers who deal with electromagnetism need to know calculus, especially Maxwell's equations. For more about Maxwell, see Math in the Physical Sciences.
What are some divisions of polygons?
There are 2 major divisions of polygons. Regular polygons are convex polygons with equal sides and length. Thus, all sides and angles are congruent, equal. For example, one of the most famous regular octagons is the stop sign used along roads in the United States. A closed polygon with 8 equal sides. The naming of the various polygons can be challenging, though. For example, a polygon called a regular triangle is also called an equilateral triangle. Another name for the polygon called a regular quadrilateral is a square. Irregular polygons are those with sides of differing lengths and variable angles. Therefore, unless all the sides of the polygon are of the same length and all the angles are of the same measure, the polygon is said to be irregular. But don't be fooled, the names for the various polygons such as hexagon, nonagon, and pentagon, depending on number of sides, don't just apply to the regular polygons, but rather to any two-dimensional closed figure with the number of sides as described by its name. For example, the two figures shown above are both pentagons. A is a regular hexagon and B is an irregular hexagon. Polygons are described in other ways, too. Convex polygons are those in which every line drawn between any 2 points inside the polygon lie entirely within the figure. Opposite from the convex polygons are the concave polygons, those that are essentially caved in, with some of the sides bent inward. If a line is drawn between 2 points inside a concave polygon, the line often passes outside the figure. Another type of polygon is a star polygon, in which a star figure is drawn based on equidistant points connected on a circle.
What is sabermetrics?
Sabermetrics is the study of baseball using objective evidence, such as baseball statistics. It uses scientifically based data and various interpretation methods to explain why teams win and lose. Sabermetrics was taken from the acronym SABR, or the Society for American Baseball Research, and was coined by baseball historian, statistician, and writer Bill James, 1949.
So how is the arrow's motion perceived?
Finally, one of the most interesting and insightful paradoxes is attributed to Socrates thus. It is called the Socrates paradox. It is based on Socrates' statement, "One thing I know is that I know nothing."
Who was Kurt Gödel?
For about 100 years, mathematicians such as Bertrand Russell were trying to present axioms that would define the entire field of mathematics on an axiomatic basis. Austrian-American mathematician and logician Kurt Gödel, 1906 to 1978, was the first to suggest that any formal system strong enough to include the laws of mathematics is either incomplete or inconsistent. This was called Gödel's incompleteness theorem. Thus, axioms could not define all of mathematics. Gödel also stated that the various branches of mathematics are based in part on propositions that are not provable within the system itself, although they may be proved by means of logical, metamathematical, systems external to mathematics. In other words, nothing is as simple as it seems, and, interestingly enough, Gödel's idea also implies that a computer can never be programmed to answer all mathematical questions.
Who first developed set theory?
German mathematician George Ferdinand Ludwig Philipp Cantor, 1845 to 1918, was not only known for his work on transfinite numbers, but also for his development of set theory. which is the basis of modern mathematical analysis. For more information on set theory, see Foundations of Mathematics. His Mathematisk Annalen was a basic introduction to set theory. Unlike most long evolutionary histories of mathematical subjects, Cantor's set theory was his creation alone. In the late 19th century, Cantor also developed the continuum hypothesis. He realized that there were many different sized infinities, further conjecturing that two particular infinities constructed by different processes were the same size.
How did mathematical analysis develop after the 16th century?
Ideas about mathematical analysis took a long hiatus after the Greeks. It didn't begin to grow again until the 16th century, when the need to examine mechanics problems became important. For example, German astronomer and mathematician Johannes Kepler, 1571 to 1630, needed to calculate the area of sectors in an ellipse in order to understand planetary motion. Interestingly, Kepler thought of areas as the sums of lines, a kind of crude form of integration. Even though he made two errors in his work, they cancelled each other out and he was still able to determine the correct numbers. By the 17th century, many mathematicians had begun to contribute to the field of mathematical analysis. For example, French mathematician Pierre de Fermat, 1601 to 1665, made contributions that eventually led to differential calculus. Bonaventura Cavalieri presented his method of indivisibles, one he developed after examining Kepler's integration work. English mathematician Isaac Barrow, 1630 to 1677, worked on tangents that formed the foundation for Newton's work on calculus. Italian mathematician Evangelista Torricelli, 1608 to 1647, added to differential calculus and many other facets of mathematical analysis. In fact, collections of paradoxes that arose through the inappropriate use of the new calculus were found in his manuscripts. Unfortunately for mathematics, Torricelli died young of typhoid. And, of course, the one name most associated with calculus, Isaac Newton, developed some of his most brilliant work during the 17th century.
What are some rules for combining exponents?
There are also rules for combining exponents, called the laws of indices. To multiply exponents with identical bases, add the exponents, such as 32x 33 equals 35, 3 is the base. To multiply like exponents, combine terms, such as 102x 22 equals 10x 2 equals 400. To divide identical bases, subtract the exponents, such as 103/10 equals 103 to 1 equals 102 equals 100, the denominator 10 has an assumed exponent of 1.
How did the slide rule evolve?
In 1620, English astronomer Edmund Gundar, 1581–1626, was responsible for constructing a scale rule that could be used to multiply. He divided his scale according to Napier's principle of logarithms, meaning that multiplication could be done by measuring and adding lengths on the scale. It is also often considered the first analog computer. But there is disagreement as to the true inventor of the slide rule. Many historians give the credit to English Reverend William Uhtred, c. 1574–1660, who improved upon Gundar's idea. About 1630, although that date is highly debated, Uhtred placed two of Gundar's scales directly opposite each other and demonstrated that one could do calculations by simply sliding them back and forth.
What is biology?
Biology is the science of life. It includes the study of the characteristics and behaviors of organisms. How a population, species, or individual comes into existence and evolves. And the interaction of organisms with the environment and each other.
What is optimization?
Optimization problems deal with the point at which a given function is maximized, or minimized. It is divided into several subfields, depending on the form of the objective function and the constraints that the maximized point often has to satisfy.
How did the Hindu Arabic numbers evolve?
The evolution of the Hindu Arabic numbers was not a straight line from India to Arabia and on to Europe. In between, the Arabic cultures had more than one number system to contend with, including at least three different types of arithmetic: finger reckoning arithmetic, counting on fingers, a sexagesimal system with numbers written in letters of the Arabic alphabet, and Indian numeral arithmetic. The evolution of the Hindu Arabic numbers continued throughout time, and includes some good reasons for why our numbers look as they do today. For example, historians believe that between 970 and 1082, the numbers 2 and 3 changed significantly, rotating 90 degrees from their original written position. This is thought to be due to how scribes worked, sitting cross-legged. They wrote on a scroll they wound from right to left across their body. This caused them to write from top to bottom, not our usual left to right. The script was then rotated when the scroll was read.